Elevator Pre-Calc, lesson 1.3, graphs of functions. Okay, so let's take a look at the first example here. So for this example, we need to find the domain first. Well, if we were finding the domain of this graph right here, that means how much of the x-axis does this graph cover? Okay, so it looks like the farthest left that this graph goes is -1. And then the farthest right this graph goes is +4 on the x-axis, right? And keep in mind right here at +4 on the x, it's not included. That's why we have an open bubble, right? So to find the domain here, right, we have, what are the x values? So at -1, we do include it because it's a closed bubble here. So at -1, we do include it. And it covers all these x values up until we get to 4, and that's not included, so we use the parentheses. Okay. Next thing, we need to find the function values for f of -1. F of -1. So all that means right here is, hey, go to -1 on the x-axis, right? Because this is like your x. Go to -1 on the x. All right. Go up or down till you hit the graph. So we've got to go down. We hit the graph right here, and then what's that y value? Well, we've got 1, 2, 3, 4, 5, so -5. So that equals -5, right? So I want you guys to understand this notation here. This is like your x, and this is like your y from the graph, okay? We need to find f2, f of 2. So that means, hey, go to 2 on the x-axis, go to when you hit the graph. We hit the graph right here. What's our y? So 4, okay? Easy. Alright, example 2 here. So we need to find the domain and range of this function, okay? So first of all, we have radical x minus 4. Okay, so we need to find the domain and range of this function, okay? So we've got radical x minus 4. So first let's find the domain, right? To find the domain. Well, remember the whole idea of domain is we can't have a negative inside. We don't want the inside here to be negative. So we need to find out, hey, when is x minus 4 going to be greater than or equal to 0? Well, that's easy. X is going to be greater than or equal to 4. So you think of a number line, right? Basically, this means that we're counting +4 and all the values greater than it, right? So how do you express this in interval notation? Well, that's going from 4, and we include it, right? Because it's okay. We can include it equal to 4. So we include 4 going to +infinity. Okay? So that's our domain. Now what about the range? We need to find the range. Well, the easiest way to find the range is to kind of sketch a graph. So what is this? So we know, let's just review real quick. Y is equal to the square root of x. We know the graph of this is like that, right? Well, what does it mean when you have this -4 inside here with the x? That means we've got to take this graph and shift it to the right 4 units to +4, right? So this graph right here is going to look like that. Well, what's our range going to be? How much of the y-axis does it cover? Well, from 0 to infinity, right? This thing just keep on getting wider and wider and wider. So our range is going to be from 0 to infinity, okay? Now, you notice here, our domain for it makes sense too. Look at this graph. How much of the x-axis does it cover? It covers from +4 to infinity, right? So everything makes sense, okay? Alright, so we've talked about the vertical line test before, so I'm just going to go through it real quick. If you've got a graph, you draw a vertical line. If it touches twice, that's not a function, right? If you've got a graph and you draw vertical lines throughout the whole graph, and it always only touches one time only, then it is a function. Okay, so that's the vertical line test, real simple. Alright, so let's take a look at example 4 here. So we need to find the intervals of increase and decrease, okay, or constant. So for this graph here, okay, now this is kind of a bad picture. I want you guys to always remember that the graph for x cubed, it kind of looks like this, right? So it never really, over here what happens is these values are so small, it gets really, really close to the x-axis. That's why it looks like it flattens out and it becomes constant, but it really doesn't. It really looks kind of like this, the graph for x to the third, okay? So I kind of exaggerated so you guys just understand the look. As it flattens out, I should probably draw this a little bit better right here. So as it flattens out, it's kind of like this, okay? Right, but it never becomes constant. Just over here it looks like it's constant, but it's really not, okay? So let's take a look at this graph. So it looks like it's just increasing the whole time, right? It's never ever going down. So our interval of increase would be from negative infinity to infinity, right? So I mean, imagine if this keeps on going down and this keeps on going up. It's always from left to right, right? This graph just continues to go up, 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 and just keep on going up, right? So it's always increasing from negative infinity to infinity, right? Over here, where is this graph increasing? Well, it's increasing right there, and it's increasing right there. So our interval of increase is from negative infinity, all right? Negative infinity to over here, -1. And then also, we have union from 1 to infinity, okay? And remember, when we're finding intervals of increase or decrease, we're always going to use the parentheses, right? Intervals of increase or decrease, always use the parentheses, okay? Now, interval of decrease, right? So it looks like it's going down right here. Well, so our interval of decrease, well, what x values does this occur at? Remember, these represent the x values. That's what I want you guys to remember. So it's decreasing at which x values? At over here, -1 to where? +1. Okay. So from -1 to 1 on the x-axis, this graph is decreasing. Okay. So make sure you guys always understand that these answers here, they represent the x values, right? Where the graphs are either increasing or decreasing. Okay, these represent the x values. Over here, where is this graph? Increasing. It's increasing right here, right? So we have, let's see, negative infinity. So intervals of increase, right? So let me write in green so it kind of matches. So we have intervals of increase. We've got negative infinity, right? Negative infinity to this value right here, which is 0. Union, and then when is it increasing anymore? Well, no, it's not increasing anymore, so that is our only answer. And then we've got intervals of decrease. So when's it decreasing? It's decreasing over here, right? Put that in pink. So change color there. So it's decreasing from what value? From 2 to infinity, right? So the x value right here is 2, and this keeps on going down, so going all the way to infinity, right? And then let's say it's constant from 0 to 2. So we have constant from 0 to 2. Now this is kind of debatable. Some teachers say, hey, you should put them in parentheses right here from 0 to 2. Some teachers say you can put them in brackets, right, 0 to 2. Because basically when it's constant, you're counting the value. Like right here, when x is 0, y is 1, so you're just counting this actual value right here. You keep on counting these values, and it's constant, it's always the same. That's why some teachers say, hey, you can just put them in brackets. For me, I'm not really concerned with that. I'm more concerned with intervals of increase and decrease. So make sure you guys always use parentheses for increase and decrease, intervals of increase and decrease. And for constant, I mean, you could give me the brackets or parentheses. I'm not really picky about intervals of constant. Okay. All right, let's talk about relative maximums and relative minimums. Okay. Now, we don't know what this graph does. All right, so we're assuming that this graph keeps on going. Right. Now, since we don't know what else this graph does, these points here, right, these maximums, right, we call them relative maximums or relative maxima because, I mean, this graph could do this, and then this point would be higher than this one, right? That's why we just call it relative, because we don't know what else the graph does, all right? And down here, these are called relative minimums, right? So this point is lower than this point, but both of these are relative minimums because, I mean, this graph would go lower over here and we don't know, okay? So that's why these are called relative maximum and minimums, okay? So let's find some relative maximum and minimums. All right, so example 5 here. So we need to find the relative minimum for this function right here, right? So with a graphing calculator, we graph this. So if you graph it, you get this right here. So this is the lowest point right here. So with your graphing calculator, you just want to use the minimum feature. If you're using the Inspire that we use in class, just go to Analyze and then use Minimum. And you can find this point right here. And it turns out the coordinate here is going to be 0.667, and the y value is negative 3.333. Okay, remember I always want you guys to round to 3 decimals for me. Okay, so that's the these are the coordinates for the relative minimum here. Well, in this case, this would be the absolute minimum. It's the only minimum for this graph since it's a problem. Right. All right, example 6 here. So we need to find any relative minimums and maximums for this function here. So we graph it on the graphing calculator and you get this right here, okay? So right here, this would be the relative minimum. Right here, this would be the relative maximum, okay? So you just need to find the coordinates right here for the relative minimum and the coordinates here for the relative maximum. So just use the Analyze tool from your Inspire. And basically you'll get the coordinates, right? So over here, for the relative minimum right here, these are your coordinates, and for the relative maximum, these are the coordinates right here, okay? The book rounds to 2 decimals, so remember I always want you guys to round to 3 decimals. All right, and then now let's review graphing a piecewise function, which you guys did in Integrated 2. So let me make a sketch real quick. So we've got a graph. Alright, so I'll graph this one right here. Now remember, this represents the domain for the graph, right? So first I'll sketch this, and this is usually the way I do it. I'll just sketch this first, and I know this is a line, so I start at positive 3, right? And then the slope is 2, so I'm going to go up 2 over 1, up 2 over 1, right? So basically, I know I have this line right here. And what happens is, then now you look at the domain. Well, the domain for this part of the piecewise says, hey, we want x is less than or equal to 1. So here's 1 on the x. If it's less than or equal to, we don't want anything after the 1. So we have to erase this part right here. So that's what I usually do. I erase this. Then I also want to look, hey, at 1 here, do I want to equal it? Do I count it? Yeah, I do. So I want to put a solid circle there. Okay. Now for this one right here, I'll graph it in green. So we start at positive 4, 1, 2, 3, 4, and then the slope is negative 1. So we go down 1 over 1, right? Down 1 over 1, down 1 over 1. So we've got this graph right here. Kind of like that, okay? And then the domain for this part of the piecewise is x is greater than 1. So at 1 here, you notice I want everything, all right, from the graph past 1, right? X is greater than 1. So I want to show all this. Anything before 1, you want to make sure you erase that if you drew like the line out more, okay? So we can't show anything before x is 1, okay? And then at 1, we don't count this point, so you want to make sure that, hey, I'm going to make an open bubble here at 1. Like that, okay? And then that'll be our piecewise function. All right, let's graph another one, kind of a more complicated one. All right, so we're going to graph this piecewise here. So I'll start with this x plus 5. So I'll start at 5. 1, 2, 3, 4, 5. And then our slope is 1, go up 1 over 1, up 1 over 1, right? So let me sketch this line. This line right here. And then what's our domain? Our domain for this part of the piecewise is -5 to -1. So from -5, 1, 2, 3, 4, 5. So -5 right here, right? To -1. That's what we want to show. So right here, I want to erase all this other stuff. We can't go past -5 on the x. -1, I want to erase all of that stuff. And then let's see if we count these values. So you don't have the equal to sign right there, so you gotta have open circles at the ends here. Okay. And then let's talk about this parabola right here. So it's in standard form, so the easiest way to graph this would be to find the vertex. So I'm gonna do the -b over 2a to find the vertex. So I'm gonna do -2 over 2 times 1, which is 2. So that gives me -1. So the x value of the vertex is -1. So I plug that in to find out what the y is. So I plug it in to find out the y is going to end up being +2, I believe. Okay? So now, let me plot that. So at -1, we're at +2. So here we go. And at -1 here, right, we do count it, so obviously we have a circle right there. So here's our vertex, right? And then since x is -1 right here, right? The domain is from -1 to 3. We don't even need to sketch the left part of this, right? So we're just going to sketch over here. So now you need to find out, hey, when x is 3, what's the y going to be? So in order to do that, you plug that into here, right? So we plug 3 into here. So 3 squared plus 2 times 3 plus 3. So you work all that out. You get 9 plus 6 plus 3. So you get 18. So that means when x is 3 right here, right? When x is 3, we're going to be all the way up here somewhere, right? So if I extend this line right here, if I make this line longer, right? Let me extend this a little bit. Right. Show it a little bit better. So I extend this up. So when x is 3, we're going to be all the way up over here. Right, I'm just gonna say, hey, let's just pretend that right there, that's 18. Okay, so we're gonna sketch this parabola. Right, it's probably not very good. So let's sketch this parabola. There we go, a little bit better. It keeps on going. Then you guys get the point. So when x is 3, it's gonna be at 18, and then we don't count the point there because there's no equal to, right? So you gotta have an open bubble there. Okay. And then let's sketch this, -4. So -4, well, I'll sketch that in green. I'll make it a little bit darker. So this is just a line y equals -4. So 1, 2, 3, 4. So here's -4, right? Let me sketch that a little bit better. Or actually, let me use this right here. So -4, 1, 2, 3, 4. Here's -4. The line with -4. Actually, I want it in green, not black. Alright. It goes out further this way. But what's the domain for this? It's x is greater than or equal to 3. So you don't want anything before 3. So we're going to erase all this stuff. Right? And at 3, we include the point. So we can have a solid circle right there. Right? So here's our graph. Okay? So let's answer some of these questions now. Just to make sure you guys understand how to answer these. So is this a function? Well, does it pass the vertical line test, right? Is it ever going to touch any point twice? No, right? So it is a function, yes. And then f of 3, right? So the easiest way is, hey, which one of these are you going to plug in? What domain does 3 belong in? Well, 3 belongs in the last one right here, right? X is greater than or equal to 3. So what's our answer? Well, there's nothing to plug in. It's always going to be -4, right? We have this flat horizontal line here. F of -4, so which domain? -4 belongs in this first domain over here. From over here, so we have -4 plus 5. That's going to give us 1. F of 5, which domain is that? Well, that's going to be this one again. So that's going to give us -4 as our answer. So what's the domain of this graph? how far left does it go? It looks like right here is the farthest left it goes, right? Which is -5. So, and then do we count that point? No. So we have -5 and we don't count it. And what's the farthest right it goes? It covers all these x values, right? Covers all these x values over here. And it covers all these x values, right? And it keeps on going forever over here. So to infinity, right? So -5 to infinity. So it covers all these x values, right? And then what's the range? How high or low does it go? Here's where you have to be a little bit careful. The lowest it goes is -4 right here, right? Now, you notice it doesn't count these y values over here, though, so you have to be careful. So for the range, all you're counting is only -4, okay? And then union, what other y values does it start including? Well, from 0, it doesn't actually count 0, right? So we're not going to count the 0, we use the parentheses. And then it goes up. Well, what's the highest up it goes to? The highest it goes to is +18 on the y-axis, right? And then also at +18, we don't count that, right? We don't count that y value, okay? So that's our your domain and your range, okay? The next thing, even and odd functions, okay? And I'll explain how to do it, how to find it graphically first, and then algebraically. Well, graphically, all right, so we have a parabola here, right? Now, a parabola, we know the parent function is y is equal to x squared, right? If a graph, right, if any graph is symmetrical to the y-axis, you notice here, if you take this part of the graph, right, if you take this part of the graph, you just flip it over the y-axis, then it's going to just lay over this part of the graph, right? So that means that it's symmetrical to the y-axis. When that happens, we know that the function is even, okay? So an easy way not to mix up the ideas between even and odd is this. We know a parabola, right? And that's very easy to remember. Everyone knows a parabola. Y is equal to x squared. Well, the squared is an even number, right? So we know the parabola, which we know is symmetrical to the y-axis. Since x squared, but this is even, this is an even, right, function. Okay. Now, an odd function, odd functions are symmetrical to the line y equals x. So I want you guys to understand this right here. And it says symmetrical to the origin. That basically the line y equals x represents, right, also represents the origin. You notice right here, if you take this part of the graph, you take it and if you kind of rotate it, right, over across this line, right, you're gonna end up with this right here, right? When that happens, right, that's considered symmetrical to the origin or symmetrical to the line y equals x. Right, when that happens, this is considered an odd function, okay? Now over here, this is not symmetrical to the y-axis, right? If you take this and you flip it across the y, it definitely doesn't lay over this part of the function, right? And it's not symmetrical to the line y equals x, okay? So this would be considered neither, right? So that's how you determine if you have a graph, all right? So let's take a look at the next example. So let's say we need to determine, hey, is this function here, right, absolute value of x, right? Remember f of x, same thing as y. Is this even, odd, or neither? Well, remember what the graph of absolute value of x looks like. It's just a v. So hey, if we take this part of the graph right here, if we flip it right across the y-axis, it's going to lay right over here, right? So when that happens, we know that it is an even function, right? It's considered an even function, all right? Now, algebraically, how do you determine if a function is even, odd, or maybe neither? Okay, so let's talk about that. All right, so algebraically, if you want to determine if a function is even, odd, or neither, basically this is what you do. You plug -x into the function, right? So basically, the function is considered even if you plug -x into the function and your answer is the function. Alright, so you basically you plug negative x into the function and you get back the function, you get back f of x. So if you plug negative x into the function and then you work it out and you get the function, that means that it's even. A function is odd if you plug negative x into the function and you get the exact opposite of the function. Alright, so you get negative f of x, the exact opposite. That's what that represents right there. Okay, so that's how you determine if it's even or odd. Now, if you don't get either of these situations, then it would be considered neither. Okay, so let's take a look at an example. Alright, so example A here. So we want to know, hey, is this even, odd, or maybe neither? So if you take negative x, you plug it into the g function, right? So we're going to plug it into the g function. So we have negative x to the third minus negative x. And then you work it out to see what you get. Well, this will give you negative x to the third plus x. So this answer here, is it the exact same? Is it the exact opposite? Or neither? Well, this is x to the third is positive, that one's negative. This x is negative, that one's positive. If you get the exact opposite, right, that means that this function here is going to be odd. Okay, let's do the same thing for example B here. So over here we have h of x, so we have h of negative x. We plug in negative x. Alright, we get negative x squared plus 1. Well, that's going to give you positive x squared plus 1. Well, we get the exact same thing, right? When you get the exact same thing, that means the function is even. Alright? And then over here, C, f of x, f of negative x. We plug it in here, so we get negative x to the third minus 1. That gives you negative x to the third minus 1, right? So do we get the exact same thing? No, that's positive, that's negative. But that's negative, that's also negative. So we don't get the same thing. We don't get the exact opposite for everything. So this would be considered neither. Okay? So that's how you determine algebraically if a function is even, odd, or neither. Alright?